Hello, Mr. Padillo.
How are you?
I'm good. How are you?
I'm good.
How's your break been?
Okay. How's yours?
It was all right. I went to see my grandma, so that was nice. But
Nice.
yeah,
Is she not around here?
nah, she lives down south a little, but people make fun of me when I say that. She lives in Goreville, Illinois, which is still south, but
We're a very tall state.
right. Yeah, very long.
Yeah. We kind of have different, like the north is like swampy, and then the south is like deciduous forest. So
Yeah.
it does, the land and the trees do change as you move.
Right. Hello, Griffin. And
Hello.
only Griffin.
Greetings. Archer.
Oh my gosh, is that a dog?
No, it's a cat.
Yes, it's a cat.
It's a frog, actually.
Very nice.
Hello.
Hello, Billy.
Hello. Griffin, come back.
How you doing?
He's letting us
I think he
out.
let his dog out.
Bring it back.
Oh no.
Griffin, go get it again.
Wait, where's Miss?
Someone's at my house.
Fetch
He will not be in my
That's
room.
my meeting.
Yeah, Griffin's cat was barking. It was really weird.
Did you get a haircut?
No.
Oh.
I mean, yes, but no, not recently.
Oh. Well, I haven't seen you in a long time. Griffin, guess what I'm eating?
What?
Guess what I'm eating?
Don't say popcorn with all your stupid stuff on it.
Oh no. Are you actually?
Oh,
Yes, I am.
No.
Well,
Stay away.
Uh-oh.
oh, so glad to see you.
guess what I'm not eating?
Well, did you get your microphone
I
fixed?
saw it.
Finn.
Well, yeah, but an apple. Not eating an apple today. I got a banana.
Oh my gosh, that's like a record. Have you ever
Well,
gone?
why
for
did
that?
you sound like...
No.
Oh, it was my wife and my wife.
How are you guys?
Good.
Good break?
Went by too fast.
It did go by really fast.
Yeah, it felt very short.
Did I not bring a paper towel? Oh my gosh.
But I kind of need stuff to do, otherwise I get this slump.
Right.
Well, today I decided to kind of switch what we were going to do. Originally, I think at the preview day, I told you guys we would review Taylor polynomials, related rates,
Right.
Implicit differentiation, and unit method. And then we'd move on to practicing derivatives again. I'm just going to switch those around. So before we get to those things, we will. What's that pizza? Where's that from?
Jax?
Dude, I just had Jack's Pizza like 15 minutes ago. Oh
Jack's-
my goodness.
Dude, are we twins?
What type is it? Is it cheese?
Half cheese, half pepperoni?
Half?
Same.
The most
We're
common.
twins. Oh my gosh, stepbrothers confirmed.
Oh my god.
Does Jack sell them half and half?
Yeah.
Yes, obviously.
Why would
Uneducated.
you buy that?
What?
So what
Why would
slice
you
are
buy
you eating now?
Pick one.
Well, my sister
Cheese?
is weird and doesn't eat meat.
Oh,
I
that's
like
weird.
pepperoni pizza. Half and half.
Pepperoni pizza smacks.
Pepperoni. Actually, I don't overly like pepperoni.
Well,
No.
pepperoni is pretty consistent.
Are you a cheese alone guy, or do you put like mushrooms?
Well, if I have anything, I like green olives and maybe sausage.
That is so weird.
Oh,
Not
green
as
olives.
weird as putting liquids on popcorn, but it's still pretty weird.
Liquid. What do you mean?
Like
Well,
butter.
but like the butter
Oh,
that
you're
you
muted.
put, to be fair.
Oh, it's so good. You
What
know
is
how
it?
Frank's their what's it called? Slogan is I put that shit on everything. I really do. I put it on everything.
I carry it
That's
around.
weird.
Oh my gosh, yeah.
When
Like
I-
something
I think
Bella carries Frank's.
When I go to breakfast, I always have my Franks with me, and I put it on. I have Tabasco. It's like
Very weird.
Not the same.
You guys are very weird.
so. I wanted to put my teeth. Just practice derivatives. It seemed like you guys were a little shaky at the end of last semester on even things like the product rule. Right, Will?
Oh, Will, he's calling you out.
Yep.
Yeah.
Well, all of you guys.
I didn't know that could happen.
Yeah, me. Wait, does everyone have teeth?
No.
Could I make
You
some?
guys suck. Yes, Mr. Sotelo.
Ow.
I thought about it earlier, but I'd already grabbed the code red. I don't want both.
Hmm.
You can't switch.
You mix it.
It's too much sugar.
Nah, you mix it.
Tea is too delicate.
Oh. Cheers.
Yeah.
Well, I got to put in my little
Oh
glove.
yeah.
Now I'm ready for the show. All right. So we're just going to practice. Oh, I better present my screen.
I think they should have given us more time to eat. I don't think we need 30 minutes in between every class because then we only have 30 minutes to eat. And
Right.
I wanted to go somewhere, but I'm like, I'm not going to have enough time.
That's
I
true.
agree. Yeah. But then which one would you like? Because would you eat before fourth? Like I'm going to eat after fourth period.
Really? I couldn't make that. So I'd
I
say
told you before.
we usually did like 20-minute classes. Instead of 30-minute passing periods, do 20.
What?
And then the
Oh.
last one is like 50 minutes.
Yeah,
I don't-
I would go for that.
I don't really
Like an
need
hour.
time before my or between my like first and second. You know,
Okay.
Like- if I could end school at like noon, pretty solid.
That would be pretty solid, yeah. But then you don't. I kind of like the break though.
Yeah, I don't mind. I don't mind either way, but I don't know.
And I go to Eggs in Paradise every morning and get their breakfast tostadas. So
Mhm.
I'm usually pretty good for a while.
Every morning.
Pretty much, yeah. 6 something. They open at 6. Sometimes I beat the waitress there.
Mr. Sotelo is there before any of the staff.
So it looks like we're all going to Eggs in Paradise Friday.
The
I don't know if
owner
I
will
can get up that
pull
early.
into the parking lot, and then she'll like walk over to my car, and she's like,
Come in.
"I saw you come, lady."
That's so funny.
Anyway, well, you guys ready to do some work?
Yeah.
No.
I don't know if Nate can do math online. He can't do
I can't do work online. It's so hard.
Let's
I guess-
see.
Try your best.
Physics yesterday, I was losing my mind. I couldn't. There's no way.
They were talking, like I was talking to Caitlin and Maddie or whatever, and they were like, "Dude, Nate looks so out of it, like that poor kid."
No, yeah, let me tell you. Physics online is not the move. I'm counting down we have 4 hours left of physics online. 4. Until we go back.
4,
Yeah,
3.
4 because, oh wait, what?
You've already had it once, right?
Yeah.
And there's 4 altogether.
We don't have school next
Wait,
Friday.
what?
What's the
Oh,
schedule?
we don't? I didn't know that. Oh my gosh, never mind. So this is
We
perfect.
don't.
That's one less
I didn't know
hour.
that.
3
No, and then
hours.
we don't have school that following Monday. It's a 4-day weekend.
Woo!
Realizing that about
One
Monday.
right now.
Will.
Bill, pay attention to math. Good, hide it.
Okay, you guys ready?
No.
No.
That's not what I wanted to hear.
Is this statistics?
Yeah, that was statistics.
Oh,
Oh yeah, it's stats. Let me tell you, that is stats.
You know what? Maybe I'll tell you guys a little bit about integrals before we
I
actually
would
get
love
to that.
to hear it.
Yeah. So if you had taken statistics, which some of you have, and some of you are in it, right?
Yes.
So who has taken it before? Is this Bella? And Marvel. Yeah, that's right. And Will and Nate are in it. So only Griffin and Adrian are.
This is embarrassing. I'm probably going to take it next year.
Yeah, I'm
What's
taking
that?
it next year.
Me being the only one who hasn't taken stats. This is so sad.
Yeah. Well, anyway, this little curve here is called the normal distribution. It represents a distribution of value. So let's say you're talking about how tall everybody is in a town. There's an average value, and most people are pretty close to that average value. That's why it's higher in the middle. But there are some freakishly tall people, but not many. And then there's some freakishly short people, but not many. So it tapers off, but it has this little knot in the middle where most people are near the average. Does that make sense? So this is called a normal distribution. Sometimes it's called the bell curve, and sometimes a more proper name is a Gaussian after Frederick Karl Gauss. And that was actually 1 year a Scholastic Bowl question, the first year I taught calc here. You know how in Scholastic Bowl they like give you clues, and like the first clue is kind of hard, and the second clue is a little bit easier, and then the third clue is like obvious to everybody what they're talking about.
Mm-hmm.
That they did that where there was like a Gaussian, blah blah blah, and then they're like normal distribution, blah blah blah, and then they're like the bell curve, and then you're supposed to get it finally after that. But so anyway, those are all the different names that it goes by, just so you know, in case you're ever in a trivia competition and they do that to you. Well, in statistics, you use this curve. You use what's called the cumulative probability distribution, and it's a probability distribution, which means that so like if I click somewhere, so let's say I'll reset this for like IQ is usually set so that the average person gets a 100 as their score, and the spread is set as 15. So 100 is the middle. Most people are close to the average score, and the standard deviation kind of tells you what kind of fall off there is. So 15 points would be a standard deviation, and then 2 standard deviations would be 30, 130. So this would be like a superior intelligence, and now they call this like very superior.
I'd be like freakishly far away, huh?
Yeah, they used to call it like genius, but they sort of changed the words now. But this is kind of like the average range, sort of in here. And what this curve can help you do is if you choose a cutoff value, like a particular, like 95, let's say, well, it can tell you that 37% of people are below IQ score of 95, whereas 63% of people are above that score. Whereas a 115 score, if you're about there, you're in the 85th percentile basically. So 85% of people have a lower IQ, whereas only 15% of people have a higher. Remember that sound?
So is that like on like standardized testing or whatever?
Yeah, they could use that for that too. Yeah. Anyway, so what I wanted to get at was that this curve, when you do statistics, you use this cumulative probability distribution to calculate. So I pick a point on this curve, and I find the area under the curve, which represents a probability or a percentage, that goes all the way from negative infinity, so all the way to the far tail. And this model, it's only a model, it's not real data, but the model technically goes out to infinity, even though all this stuff makes like no contribution because it's so small. but it technically goes out to infinity in both directions. And what we constantly do in statistics is we try to figure out what percentage of the people are to the left of this mark and what percentage of the people are to the right of this mark, where the percentage of the people is represented by the area underneath the curve. The total area underneath the whole curve is 1, which represents 100%. And then as a decimal, this gives you a percentage if you calculate the area underneath the curve. As you can see, this is about 17% of the area underneath the curve, where it's 83% to the right. Does that make sense? All right, so when we calculate integrals, so let's say this was a function that we had. So we had a function, I'll show you what the function looks like. This is what the function looks like. It has a constant here, which basically sets the area so that it's equal to 1 underneath the curve. And then it's basically an exponential. It's basically, the parent function is e to the minus x squared. It's actually kind of translated, so it gets shifted to the right from 0 to some mean value. And, you know, it's not, don't overthink it, but basically it just creates a little bump somewhere. And then e to a negative exponent is exponential decay. So as you go further out, it just decays to 0 in either direction because it's squared, so the sign stays the same. So it's always negative either way you go. But there's this one part in the middle where it's kind of significant in size, but it gets crushed as you go away from the middle. So this is, that's the Gaussian distribution. I mean, most students in statistics don't work with this equation. They just use the calculators. But this curve here is the cumulative distribution function, which is what people use their calculators to use. And this represents the integral of this curve. So this is called a sigmoid function. It's also called a logistics curve. And it basically represents saturation. So when you're to the left, you're at 0. And then you rise to half the saturation level. And then once you reach saturation, you can't go beyond that. So a lot of times it represents like disease spread. So like nobody has a disease and people start getting infected at an exponential rate. And then once nearly everybody's infected, it tapers off to some level. So that kind of represents that. If you think of the slope of this curve, the derivative of this curve is this curve, whereas the integral of this curve is this curve. So integrals are, there's multiple interpretations of integrals. They can be thought of in more than one way. One of the ways that can be thought of as the inverse operation of derivatives. So who remembers what the derivative of sine is?
Cosine.
Cosine.
Good. So what do you think the integral of cosine would be? The integral of cosine will give you the thing which, if you took the derivative of it, would give you cosine.
Okay, wait. Integral?
Inverse of the derivative.
Inverse of the derivative. So
it undoes what the derivative does.
Negative cosine. Or negative cosine over 1.
So the integral of cosine is the function which, if you took the derivative of it, would give you cosine. So what can you take the derivative of to give you cosine?
Sine.
Yeah.
Negative.
No, just sine.
Sine.
The derivative of sine is
Sine.
cosine, right?
We got it. Yes.
So the integral of cosine is sine. It undoes it. It goes the other way.
Gotcha. So it's just like backward.
Yeah.
Okay.
So what would the derivative of x squared be?
2x.
Good. So what do you think the integral of 2x would be?
Integral is x squared.
Yeah.
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 Makes sense? So that's actually called the fundamental theorem of calculus, is that the integral is the antiderivative, sometimes they call it, that the inverse operations. That's one interpretation of the integral. Another interpretation of the integral is the area underneath the curve. So if I took the integral from negative infinity up to 85, let's say, oh, I'll just type it in. The integral of this curve from negative infinity up to 85 will give me the area underneath the curve all the way from the left to here. And that value would be 0.1587. So another interpretation of the integral is the area underneath the curve. Do you follow that? So if you think about this, if you think about this curve, think about little skateboard guy, okay? What's the slope? So remember the way his little skateboard is going, the tilt of it gives you kind of like the slope of the line, of the tangent line at that point, that touches at that point. So what's the slope when he's way off to the left, riding on this curve when he's way over here? How is he tilted? Like flat? Yeah, so the slope is 0, right? So he's flat here. And then as he, well, let me use this other curve actually. Let's do this curve. Let's do the blue one. Imagine he's riding the blue curve, okay? You got little skateboard guy. What's the slope of his skateboard when he's riding the blue curve all the way on the left side here? 0, right? That'd be a flat line. If he's going up, it becomes positive. If he's tilting down, it becomes negative, right? So he's at 0, right? 0, 0, 0, 0. And then he starts to tilt up a little bit, right? And so that's a small positive value. And then if he goes further, it becomes a steep positive value. And then it turns steeper still. And then here he's at his maximum steepness, right? He's as tilted as high up as he's going to get. And then he's still tilted up, but he's starting to tilt down a little bit more than he was before. He's starting to tilt lower, still pointing up, but lower. And then he's starting to flatten out. And then he finally goes flat again. So he's back to 0, right? Well, that's what gives you this curve. It's 0, 0, 0, small positive, max value, small positive, back to 0. So it turns out that this is actually, this thing is the derivative of this thing, right? So the rate of change is represented here. Whereas, now think about the area underneath the curve from negative infinity up to this line. So this is now that I'm integrating this function up to a certain point. So I'm basically collecting the area underneath the curve all the way from the left up to this point. So at first I have nothing, right? There's nothing to the left. And then as I move to the right, I get a little bit more, a little bit more, a little bit more. And then I start growing at the fastest rate possible when I start to get towards the middle. So I'm at 30%, 43, 50, almost 70, 78. So it grew very fast as I went across the middle because I accumulated a lot of area. But now as it tapers off, I'm accumulating area at a lower rate, right? So 97, 98, 99, and then just decimals after this until nearly everything is underneath the curve. And that's approximately 100%. Well, the integral of this curve, like I said, the inverse operations, is this curve. You have nothing, 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 nothing. And then you start to accumulate area very quickly. And then you still accumulate area, but it's slowing down once you get past the hump. And then you pretty much have all the area. You've accumulated everything. So that's another interpretation for the integral, is the area underneath a curve. And that's how those curves are related. They're actually related by calculus. So the stats students don't really do calculus. They have the calculus pre-done for them in their calculators, but they're using the results of calculus to do statistics. But it's actually calculus that by which we know these things. So, but I just wanted to give you that visual that the area underneath the curve up to some point all the way from the left is an interpretation of an integral. It gives you the area underneath the curve. Does that make any sense to you guys? All right. So one thing to point out is that, let's see, if I have a function and I have an integral, and you can write them like, so this is my f of x. And let's say I want to take an integral from point A to point B of f of x. And you always have this little dx. I'll explain that more in the future. But it basically would give you the area underneath the curve between those 2 points. You can kind of think of it that way. That it just sums up the area. Does that make sense? If I had another curve like that, and I integrated from A to B, and you put the limits up and below and above this long elongated S, that's the symbol for an integral. Going from A to B, you would collect this area. You'd calculate the area underneath the curve. And let's say it's like, I don't know, 10 units. And then you would, this area, because it's underneath the line, let's say it's like -3 units. Because it's underneath the line, it's a negative area. So the integral would be something like 7. Because the area underneath the curve contributes as a negative contribution. Does that make sense? Okay, so I just wanted to preview what we will eventually get to. I usually like to start the integral calculus right at the halfway point, but we're going to start it a few weeks late. So
the songs, when they say like integrate by parts, do they mean like they take that positive chunk first and then that negative, or? No,
that one, it's I can explain that kind of quickly. You have the, if I had 2 functions and I wanted to take the derivative of their product, you would use the product rule. So you prime v plus uv prime. So that's the product rule, right? You guys are okay with that? Hopefully. We're actually going to practice these rules of differentiation this week. Well, you can rearrange this for, let's say, this guy. So I want to get that thing alone. So I'm going to subtract this thing, u prime v, from both sides. And I can find that u v prime, or u times the derivative of v, is equal to u times v derivative minus the derivative of u times v. So I've just rearranged it. Now, if I make an integral sign on these things, so if I take the integral of each term, then the integral, remember, and the derivative sort of undo each other. So on this thing here, that's the derivative of the whole thing, the integral will sort of undo that derivative. So this becomes the right-hand side. Well, this just stays the same. They call this dv when they write it in the integral form. The derivative of v equals, then these undo each other, uv minus the integral of v du. Does that make any sense at all? A little bit? So integration by parts is this formula. It says that basically if I have an integral of something like natural log of x times e to the x dx, let's say that's my integral. Well, that's not one of your basic integrals, so it's like kind of hard. So well, maybe let me do a simpler one so that maybe you guys can actually follow it a little bit better. Let's do x squared e to the x dx. So remember, the integral is the opposite of the derivative. It's the inverse. So whatever I take the derivative of, if I take the derivative of something and it gives me that, x squared times e to the x, that's what the integral of this should give me. It gives me the thing that if I took the derivative of it would give me x squared e to the x. So what could I take the derivative of that would give me x squared times e to the x? That's hard, right? That doesn't come easily to anybody. So, so that's a nasty integral, and it's hard to do. So let me just say e, just to make it a little bit simpler, just to make sure it goes okay. X times e to the x. The derivative of what would give me x times e to the x? I don't know. That's tough. But integration by parts says, think of, and here's where they use liate. Do you remember that from the song?
Yeah.
That stands for logs, inverse trig, algebraic functions, trig functions, exponential functions. And if you remember from the song, this is how I choose my u, right? So you basically say, okay, I need something to be in my integral. I don't want to do this integral. This is a hard integral. So I want to replace it with a non-integral and an integral that I hope is easier to do than the one I started with. So, so I've got two functions here. I got an x and I got an e to the x. X is an algebraic function, while e to the x is an exponential. So I want to choose something to be u. So this integral of u dv. What's my u and what's my dv? Well, how do I choose my u? I use liate. So do I have any logs in this in this integral here with x squared e to the x? No. Do I have an inverse trig function? Do I have an algebraic function? I do. So that's how I choose my u. My u is x. And my dv must be the other bit, e to the x dx. So this is called integration by parts. So
What
yeah.
was the T and E again?
The what?
Like, what is the T and the E again for? Because I was going to write it down.
Trigonometric, so like sine, cosine, tangent, where I is inverse trig, so like arc, cosine, arcsecant. E is exponentials.
Okay, thank you.
Mm-hmm. So I use Leate to choose my u. I'm going to identify x as my u, and I'm going to identify e to the x dx as the rest of it, the dv. So u, I'm just going to take the derivative. What's the derivative of x using implicit differentiation? That'd be dx. I wouldn't just say x, I'd say dx, or 1, I'd say dx. And then I'm going to integrate, that is undo the derivative of dv. That'll tell me that v, well, the derivative of what gives me e to the x?
E to the x squared.
No.
No.
What's the derivative of e to the x? You remember?
X to the E -1.
No, you're doing the power rule.
Oh,
Isn't just EX?
It's e to the x, right?
Yeah.
There you go. Yeah. The derivative of e to the x is e to the x. So the integral undoes the derivative. So when I take the integral of e to the x, I'm asking the derivative of what gives me e to the x? Well, it's just e to the x again. So v must be e to the x. Is this okay so far? We're jumping way ahead, but that's okay. So basically, I took this integral that's ugly, and I don't want to do it. I don't know how to do it, and I'm gonna say this is my derivative of u times dv, but u times dv is equal to u times v. So this thing is equal to, I'll change colors. That's the same as my u times v, x e to the x, minus my v du, integral of v du. So the integral of v is e to the x, and my du is dx. Okay, well, we just did this. What's the integral of e to the x?
E to the X.
Yeah, e to the x, right? So that gives me e to the x e to the x minus e to the x. So I just did my integral. I had a nasty integral I didn't know how to do, but then I used integration by parts to replace it with a function that's not an integral, and then an integral that's hopefully easier. And then if I can do that integral, if it's a simple integral that I can do, or I have on my equation sheet, then I can do it, and I get the integral completed. The one thing that we haven't gone over this, but the only thing, like when you take a derivative of x squared plus 1, well, the derivative would be 2x, right? So, well, if I say the integral of 2x should give me the thing that, if I took the derivative of it, okay, if I took the derivative of something, what would give me 2x? It'd be x squared. So I've lost the fact that there was a plus 1 here, or a plus 2, or a plus 5. I don't know about the constant. So I could be off by a constant, so I have to put a plus c. So because if there was a constant there, I've lost it. I've lost all information about it. So I actually have to put plus c to show that there could be a number like +1, +5, -11. I don't know. But this is integration by parts. It's a way of substituting the integral that you have with something that might be easier using the product rule. And when you do integrals, you'll learn that you always have to add a constant that you might not know about. So I know that's a bit advanced. That's ahead of where we're at, but that's integration by parts. And that's why they're like Liate is how I choose my U. You know, like it's just a pneumatic thing to help you remember the procedure. We will definitely cover that in more depth in the future, but we're going to start with simple integrals so that you know how to do those. But I wanted to give you a little bit of a heads up about what integrals, how to interpret an integral. They're the opposite of a derivative. They sort of like x squared and square root of x. They're inverse operations. Or e to the x and log of x. They're inverse operations. Well, the derivative of a function and the integral of a function are inverse operations. Now, I'm going to erase this if that's okay. I'm recording, so you can watch it again. Let's say I have a little speedometer, right? And you watch the needle kind of move around. And let's say I gave you a graph of this velocity versus time. And let's say the graph went something like, who knows what these units are? All right, so do you guys know from physics that the area under this curve represents the, what does that represent?
Something.
It is something in reality.
We haven't gotten that far in physics yet, so
Okay.
maybe we have. I don't know.
Well, what happens when I take the units of area under the curve? Can you find the area of this triangle?
Yes,
Do it.
7.5.
Good. That's the area underneath the curve, right? Well, how did you do that?
Sides.
I'm a wizard.
No, what specifically did you do?
Well, you see, there's a 5, so the bottom's 5. And then you times that by 3, because that's the height of the triangle.
Uh-huh.
Then you divide that by 2.
Yeah. So 2 has no units. 3 has units of, what are the units on 3?
What?
V.
What units?
I don't see any units.
Let's say these are meters per second.
Then
Seconds. Yeah.
meters a second.
So yeah, meters per second. And what are the units on 5?
Seconds.
Seconds.
So what are the units on the 7.5?
Okay.
Meters.
Meter per second squared.
Second squared.
No,
Oh, what?
Should be just meters then, right?
it's just meters, right?
Witchcraft.
Wow.
So this tells you, if you know this was my speedometer, you know how far I traveled in that time, right? But you don't know where I started. You don't know if I was at 10 meters from the origin when I started, or 1 meter from the origin, or 11 meters to the left, right? So this tells me the distance I went, but not from, I don't know where I started. So my final position will be 7.5 plus, I don't know, my initial position. But I don't know my initial position. So when you take an integral and you find the area under the curve, you're undoing the derivative, which is your rate of change. And what you're getting is a quantity but you don't know your starting quantity. You just know the change in your quantity. So you have to add a plus C always, which represents where you start, your initial condition. You know, like, does that make any sense?
Yeah.
Okay.
Not at all.
At least Will's honest. That's what we like to see.
I thought I was teaching you something here. Well, so the idea is that if you have a rate of change, you kind of have a speed. Well, if I have a speed, I can figure out your change in position. But I can't figure out your specific position because I don't know your starting point. Right? So we have to add an unknown number, which represents an unknown starting point. And that's why when we take integrals, usually we have to add an unknown constant to find, because we don't know, we can't account for it. So that's why in the songs they're always like, they're always talking about forgetting C, that people always forget to add C. C's be killing me. That one's a double entendre because he could be talking about his grade, or he could be talking about the unknown constant that he always forgets to put plus C in his integrals. So that was a good lyric. But I know you guys were thinking about starting your lyric writing, so I thought I would give you a little bit of a heads up about what integrals are about and what they, what is Leate for, what is integration by parts. Integration by parts is, I'm trying to think of something analogous like an algebra. What's like something in math that if the expression is kind of hard, you can write it in a different way, and it makes it easier. I'm trying to think of a good analogy.
Slater.
No. Maybe
Photo math.
maybe completing the square. Maybe completing the square.
Is someone writing this down? Because I know I'm not.
I'm recording it.
Joke's on me then.
So like completing the square, if I have like y is equal to x squared minus plus 4x minus 7, let's say. How would I plot that? I don't know.
Box.
Like what?
Like your little box method.
Box method.
Yeah.
I don't know the box method.
Is that not what it is? The one that's like the gene thing that you do in biology?
Punnett square.
Yeah. We did those in pre-calc for these. Or like the magic X or whatever.
Oh, you're factoring.
Oh. Ignore me.
That helps. The Pythagorean or the quadratic formula could help you. But probably the easiest way is to complete the square. So, you just say x plus 2 minus 2 squared is 4. And then that replaces this. That's completing the square. And then you still have the minus 7. So you can say, 4 and 7 makes negative 11. If I bring it to the other side, it's y plus 11 and equals x plus 2 squared. So I've completed the square. I have it in vertex form, and now I know that the vertex is at -2, -11. So it kind of helps me know where I know where to put the parabola. It's just like a little way of taking something in one form and rewriting it in a different form so that I can do it more easily. I can do the graphing more easily. So I would know that I would go to -2, -11, and I would go, up over 1, up 1, over 2, up 4, and there's my parabola. So it's just it's a way of changing the form of something, so it makes it easier to do. That's basically what integration by parts is. You have a nasty integral, you write it in a different way, and now it's easier. It uses the product rule. It's based on the product rule, but you basically just memorize the procedure, and that's how you do it. Does that make any sense? A little bit? I'm just trying to, it's not like I'm going to quiz you on this anytime soon. It's just that I want you to have a sense for the nature of it. Like, what is integration by parts? Well, it's just a little technique to make integrals easier. Why do we add C? It's because we know if we know the rate of change as a function, then over an interval, we can know how much change is accumulated, but we don't know the starting place. So you have to put in the unknown because you don't know what the initial value was. So that's why there's always a plus C. Integrals, what are they? Well, they undo the derivative, the inverse operation of the derivative, and they also can be interpreted as the area underneath a curve. So if you want to calculate the area underneath this funky looking curve, you can integrate the function. So that'll give you the area of the shaded region or whatever. Just so you have some intuition about where we're going. We'll make sure you won't test on this until you've had more practice. We'll go over this more formally. Is that okay? All right, so today I guess we just went over the concepts of integrals a little bit. Next class, I think I'm just going to give you a bunch of derivatives. I said this last class. You can ask like the most profound questions, like, how do you guys feel about the state of the world today and the way it like affects everything, and then you just look at your class and they're all like, yeah, thumbs up, yeah. I'm just like, damn it. Anyway, I should make a video about that. Just profound questions with just people like, yeah.
Make a YouTube video about it, and then it'll go famous.
Yeah. You have your 15 seconds of fame.
Yeah, like TikTok. But whatever.
Yeah.
That's all I've been waiting for.
For you.
Yeah.
Just make a Vine on it.
Just be like, how do you guys feel about the state of the world? And we'll all just be like,
yeah. All right. Well, I guess I'm just showing you a blank screen, aren't I? I can shut that off. All right, so next class, a lot of practice with derivatives, basic rules. Just make sure you guys are sharp with that. And then we will review some of the topics that we didn't test on last semester. And then we'll be fast moving into a test on that. And then once we get that out of the way, we will start integrals. Sort of conceptually at first, but then, more formally. Kind of like derivatives, we sort of started with skateboard guy, and then we started doing them, and then we found applications for them. Same with integrals. Sound good?
yeah.
Yeah.
I feel like we should pick out a song soon
Yeah.
so we can start thinking about lyrics.
I thought you were writing the lyrics.
What kind of song?
That Kanye.
A rap song?
I feel like a rap would be easiest because like then all of us would be able to rap. Like not all of us would be able to sing
I
a
definitely
part.
can't rap.
Yeah,
He's
what
just
is
talking fast.
Nate cannot.
You guys already know in physics. I had the highest note. I can hit the highest note.
Well, sometimes rap artists collaborate with singers.
That's true.
Yeah, we could do
Oh.
first song off the top of my head
Umbrella.
is that's
Oh.
really good.
Rihanna
Yeah,
and
there you go.
Jay-Z, right?
Alicia Keys and Jay-Z. In New York.
Oh, but
You can hit that note, Nate. Rihanna and Eminem.
we should get Eminem to collaborate on this.
We
I
already
think
have
he would.
Eminem.
I think Snoop Dogg would. He's always doing stuff for schools.
We should get Benji to collab.
Yeah.
Oh yes.
Benji Ave.
Oh, God.
We'd instantly go viral.
Yeah, that'd be funny. Yeah, you guys can do whatever you want with that.
We'll get MGK and Eminem on the same song so that their beef is like coming to head with us.
Do it with guys. If we collab with Benji Ave, all of his 21 monthly listeners would listen to our song.
Hey, that 21 a month. Like
That's
he's on the
weird.
come up. He's on the come up, Griff.
Yeah, I know.
We would get if we did it ourselves. So
Do you guys have ideas?
No.
for the song. Well,
Is that what we're going to do? Rap and singing?
yeah, I feel like that's a good idea. We'll cover every end of the spectrum, We'll get a scat singer.
What?
Skiddly doo bop.
Hey.
Who's going to do that part?
I'm actually
Mr. Sotelo.
What's that?
Is Mr. Sotelo gonna have any part in our song or no?
He's the
Yeah.
lead vocals.
Obviously, like
He's going
you know,
to.
some of the videos
Have
have like
to.
the acting part
Yes.
at the beginning. We definitely need that.
Oh, yeah.
Oh my
the,
God, yeah, we
the
should-
setup.
Yeah, we have to have the setup, so you're gonna be a part of that.
Oh,
Yeah.
Marvel.
Oh,
Oh,
Gundam style.
Cloud goggles. Oh my God. Wait, check this out.
oh, she's pulling out her sunglasses.
Oh, but
Her
those listen to
bows.
music.
These are the
Oh.
Yeah, well, these are made of wood.
Oh.
I think you win.
Wood and plastic.
Oh.
Boom.
Boom.
These help me see, so.
Wait.
Oh, so do
Oh,
these.
never mind. Did not see those, they were hidden.
Marvel always has an ace.
Marvel's always prepared. He's always strapped.
Double glasses.
Oh, God.
He's got a gun. He's
What?
got a gun.
Marvel.
Nate left.
Griffin, I will do it.
I'll do-
Marvel has one ready to go. That's
I
funny.
I have
We
more fun too, Marvel.
You could, Nate.
Oh, my God, there's multiple guns.
I have a fidget spinner.
Oh, I can't compare.
I got a deck of cards that I can throw.
I have a
I
tiny
have
plant.
3 fidget spinners.
I
can
have
remove two
chopsticks.
from a keyboard.
3 of them.
Oh, actually,
Oh,
I got a knife.
where's that?
Oh
I
yeah,
have
and
a
the mask.
butterfly knife.
Why do you
made
guys have all
out
these
of
on
leather.
hand? I have to
Oh.
turn down the close-up on mine.
Adrian
I got
Hey,
Loki has a moose head on her wall.
yeah. Hey, you never know when there's gonna be a robber coming down my step.
can
What do
hide
I
it.
have? A knife.
I'll just
You
intimidate him
never
with
know. I'm
that.
strapped.
That's big.
Actually,
It's like half the room.
Marvel's gonna have like a rhinoceros head.
Marvel's just gonna pull out a sword.
Oh, he's got his gaming set
you
up.
know what?
Oh.
You know what? Nate Chu can play this game.
Oh yeah. Well, mine's not sharp, so boom.
Well, mine's also dull, but it's
Well, mine has rust, so that's called tetanus. Infection,
Mine's-
baby.
mine's black.
I bought a.
Oh,
I
never mind.
spent $60 on a.
Mine has a cool dragon design.
Like 12.
On what age?
On like this board from the show when I was like 12. So, yeah, I don't know. I think I win if I wanted to go get it. Just out there.
Well, class is over, so I'm gonna leave.
Goodbye.
You
Sounds
should
good,
bail
man.
him early.
Yeah.
We even. Oh, okay, he's gone.
All right.
Okay.
I will see you guys Friday, right?
I will see you
Yeah.
tomorrow.
All right, so,
Friday.
have a nice day today and tomorrow until I see you again, and then I'll tell you that. Bye, Griffin. Love
Bye.
you.
What?
Love you.
Of course.